there must be a net force upward. That means on everything, right? The person, the scale, this elevator, everything has to have a net force upward. This is where we focus in on the person, just like we did before. Now, a common misconception is that there is somehow now 3 forces acting on the person. There aren't. It's the same 2 as before. Gravity pulls down on them, and then the scale pushes up on them. The same 2 as before, normal force and gravity. The only difference is this. If you have the force of gravity acting down on the person and the normal force acting up, they are now out of balance. In fact, I can infer that the force of gravity has to be not as big as the normal force now. The upward force has to beat the downward force if you are to have an acceleration upward. Okay? So what we have now is this. The upward force has to exceed the downward force. If you want to see how that falls out of an equation, this is why I did this in such a long-winded way, because it's the same equation, except now my acceleration isn't 0. So I could write down the same equation. Only now I'm very careful to leave the acceleration in place, to acknowledge the fact that the 2 forces that are acting cannot cancel. They cannot cancel because I know the person is accelerating. And anytime anything's accelerating, there has to be a net force. And if there's a net force, it means the forces that act on it do not cancel. There's some left over. So you can solve here for the normal force. And of course, if the acceleration here is positive, which this equation assumes that upward is positive, then you do indeed see that the normal force ends up being bigger. The form of the equation is that the normal force is mg plus some crap, right? So that makes it more. The normal force exceeds mg. It's got an extra bit. Okay? So, I mentioned we can cleave a difference between the normal force and gravity, and the scale reading goes as the normal force. So what will happen here is that the scale will read a larger value than when you're using it how you're supposed to. You can get in an elevator, stand on a bathroom scale, and if that elevator is accelerating upward, it will read a larger value. And hopefully that convinces you that the scale really does read normal force, because I assure you the Earth is not pulling down on you harder because you decided to take an elevator ride. Okay? The force on gravity on you is the same as it was. It's the same here as here. So this is constant. That does not depend on your ride, but because of your ride accelerating upward, this has increased. The floor pushes up on you harder than it would normally. Okay? The scale reads the normal force, and to say that it weighs you is basically to rely on the fact you're using it how you're supposed to. You're using it with the acceleration being 0, and therefore it's accurately measuring a force which happens to coincidentally be equal to your weight. Now, you don't even have to have an elevator for this. If you have one of those analog scales with a needle, just try accelerating in place, go like this. And you can get the needle to jump around. I assure you the Earth is not suddenly pulling on you differently. But the scale is pushing up on you differently, right? That's what's changing. So a scale reads normal force. So it seems like kind of a parlor trick to just fool the scale into reading something that it's not supposed to, but it's not just a trick for the scale, it's a trick for your mind. Because when you walk around, you do not judge how heavy you feel by the force of gravity pulling down on you. You judge how heavy you feel by how hard the ground you're standing on pushes up on you. You also judge your own how heavy you feel with the normal force as well. It's not just what the scale does, it's what your mind does. Okay? So how you feel can differ from what you actually weigh. And so we also say that your apparent weight is also the normal force. How heavy you feel, okay? So apparent weight as different from your actual weight, which is weight being another name for the force of gravity. Now, let me try to convince you, if you haven't ridden in a lot of elevators. Okay, so I hit the elevator, I get in, and for the moment that the elevator accelerates, you feel heavier. Has anyone ever experienced this? Okay, I assure you the Earth did not suddenly decide to pull on you harder. The Earth doesn't care. It pulls on you with mg, always. That's your actual weight. But the floor suddenly pushed up on you much harder than you're used to. It didn't just hold you up, it actually exceeded your weight. So that's not how you perceive it. You perceive it as, I feel heavy for some reason. What it is, you get into the elevator, it's stationary, and of course you have inertia, right? Your body wants to stay at rest. So you're standing there waiting for something to happen, and your body has inertia, wants to stay at rest. And suddenly the floor just decides to start accelerating up into you, right? Now, you don't perceive it as the floor is kind of trying to come up and smush my feet. You perceive it as I feel heavy, right? You judge how heavy you feel by the amount that the floor pushes up on you. And in this case, you feel heavier because the floor is pushing up on you harder, okay? So remember, if you're asked about apparent weight or a scale reading, you're being asked about the normal force, which may not be the same as mg. We could, of course, do the opposite. What if we accelerated downward? So what if you're in an elevator accelerating downward? Well, that means that you have to have a downward net force, right? Same two forces acting on you, force of gravity and the normal force, but now they're out of balance the other way. Force of gravity, same as it always is. I assure you it doesn't care about your elevator rides, but the floor does not push up on you as hard as it usually does, because you have to let the downforce win now. If you're going to have a net force and acceleration downward, you have to let the force of gravity be the bigger one. So now n is less than mg. So what does that mean? It means that the scale reads less than you're used to, and you feel lighter than you usually do. Okay? Has anyone ever ridden an elevator and felt these things, or am I the only one? Okay. You feel heavier when it accelerates up. You feel lighter when it accelerates down. Okay? We can even go to the extreme. What if our acceleration is not just any old thing, but the elevator cable snapped, and you have a very particular acceleration downward, which is free fall. So let's plug it into the equation. The forces N is up, mg is down, and overall we should expect a downward acceleration, right? Of not just any old thing, but minus g. What is the normal force here? It's not only less than your weight, it is exactly what? 0. So you have achieved a state of apparent weightlessness. Okay? You will not only feel lighter than usual, you will feel like you're floating in air. Okay? So what's really going on? Well, if you like to think of it from the outside perspective, so someone watching outside, watching you plummet to your doom, what they would see is a scale in free fall, and your feet free falling on top of it, right? We talked about everything accelerates the same, right? You drop any two objects, they fall together. Well, now it's the floor of the elevator free falling out from underneath your feet as fast as you can fall towards it. You're both in free fall. But that's not what you see. You feel like you're just floating above the scale. Okay? Question?
What about air resistance? That hasn't been
Oh, this is all neglecting air resistance, right? Yeah, so taking that out because that has a major bearing on a lot of things we talked about. So we have achieved apparent weightlessness. So you might say, well, oh, that's fake weightlessness, okay? That's not like real weightlessness. You'll find out really quick when you hit the bottom of the elevator shaft that gravity didn't turn off. You'll have a second there before you meet your doom. You might say, well, that's not real weightlessness. Like, for instance, you see the astronauts in the International Space Station, right? And they float up there for days, right? There's an experiment going on right now where they sent some guy up there for a year just to see how this affects his physiology, right? Well, it's the exact same kind of weightlessness. Okay, let me talk about what happens when you're in orbit. So here is an astronaut. They're in the International Space Station. Here's the Earth. This is getting a little bit ahead of where we are now, but what is orbit exactly? Orbit is a state of perpetual free fall. The only force that's acting here is the force of gravity. And those astronauts are very thankful for the force of gravity because they have a substantial sideways motion, and if they didn't have any force at all, Newton's first law would take them who knows where. So Newton's first law means that if the net force is 0, they would go at a constant speed in a straight line. See you later. The force of gravity is what holds them and hugs them to Earth. In fact, they're in a state of perpetually free falling. It's like this. They get pulled in an arc-shaped motion, just like you've seen, right? We talked about the arc-shaped motion when you fire something horizontally off a cliff. Except here's the difference. You're falling, 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 falling. Oh, wait, I'm not any closer to the Earth than I was before. So you just keep going around. So you're in a state of perpetual free fall where you're continually falling and you just happen to keep missing the Earth. That's what orbit is. Okay? So it's the same exact type of weightlessness that you have in that elevator when somebody cuts the cable. The only difference is that while you will only experience that apparent weightlessness until the elevator hits the ground, this can be experienced indefinitely. It just happens to have, the people in orbit happen to have a sideways velocity that allows them to continue to fall indefinitely. Now, as to the exact details of how the speed you have to go matches up with how much force you need to keep you there, we'll get to that. I think it's homework 6. We'll talk about circular motion. But for now, I just want to introduce you to this concept that apparent weightlessness, as long as you are acted upon by gravity only, you will feel apparently weightless, because how heavy you feel is based on the normal force. And if you can get the normal force to turn off, then you will feel an apparent weightlessness. Okay? They never ever say this when they're on the news or whatever, right? The astronauts are experiencing weightlessness, blah, 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 blah. It's astronauts are experiencing apparent weightlessness. Okay? The force of gravity up here, I'm not going to sugarcoat this. It's a little less. It's about 90% of what it is on the surface. But 90% of the force of gravity is still a lot of force, okay? Force of gravity does not turn off up there. It's still substantial. The thing that allows them to experience apparent weightlessness is the fact that they are in perpetual free fall. Are there any questions on that? Okay. In fact, you can simulate this for prolonged periods of time, even here on Earth. If you've ever been to the amusement park, there's a ride called the Drop Zone, whose purpose is to do this, right? You guys know what the Drop Zone is? It's like a tall tower, and it has seats around the outside, and then they basically just give you a couple seconds of free fall, right? Before they safely decelerate it, right? They don't let you just hit the bottom, okay? So if you've ever been on that thing, it feels like your internal organs are like up here, okay? And it feels like you're just floating above your seat, okay? It feels like you need the seatbelt just so you don't go drifting away, okay? That's because you're experiencing apparent weightlessness. And the reason why your organs feel like they're up here is, of course, because of inertia, right? So if your organs are in here, suddenly you accelerate downward, and your organs stay where they are until your body, your outside casing, tells you, hey, we're doing something else now, right? Okay. Obviously, there's only so tall you can build a tower. So, for instance, you're NASA and you want to get astronauts used to weightlessness or apparent weightlessness. All you need to do is figure out a way to get the force of gravity to be the only force. They have a plane which does this. This plane basically works like this. You're in the plane, and then they just fly a path that is exactly the same as projectile motion. So basically, it's the same thing as shooting you out of a cannon, but then flying a plane around you as you are flying through the air. Okay? So if you're flying through the air under the influence of gravity only, and there's a plane that just happens to be flying around you, you're not going to touch the walls or the ceiling or anything. It's going to feel like you're floating there. But the reason why is because the normal force on you is 0. It's because you're flying a path that's just due to the force of gravity. So this plane, I forget what it's called, is some X3Q7 type designator. The nickname of it is the vomit comet because when you're not used to this, you can really start to feel nauseous, right? Your stomach is not where it normally is as pulled down by gravity, okay? So what they do is they fly some arcs, they pull up, and they do it again, pull up, and so on and so forth, and you can kind of get your training for before you go up to the space station. Are there any questions on that? Okay, so that's a little bit about apparent weight and apparent weightlessness. So if you've never given it much thought, how heavy you feel is not tied to the force of gravity at all. It's tied to the normal force. And I guess in the next 3 minutes, let me at least set up our next problem so that I can start with it on the board next time. That is the official end of homework number 4 material, but no big kind of sea change in what we're talking about. The next problem doesn't even introduce friction yet. It's just a further application of the force of tension. So obviously today we've been focused on applications of the normal force, inclined plane, apparent weight. Let's do something a little more advanced applied with tension. This is going to be my pulley problem. If you plan to be an orthopedic surgeon and put people in traction, you should know a little bit about this kind of thing. So here's my problem. I have a pulley. It's just basically a spinning disc. It's mounted to some wall or something like that so it doesn't move. And I'm going to drape a rope over it. And I'm going to put a mass on either side. The mass, those two masses are the only mass in the system. So we're going to neglect the mass of the pulley, the mass of the string, everything, all the inertia is in those masses. That's an approximation. I'm going to give you the two masses, and I'm going to ask you for how each of them accelerates. And in fact, that proves to be enough information to do this. If you just are given the two masses and that they're connected by a massless rope over a pulley, then you can actually solve this. The only function that the pulley plays here is to redirect the force. It allows us to bend the path of the string without any adverse effects otherwise that we need to worry about. So let's see how many of these steps we can knock out in the next 60 seconds. Step 1, object of interest. We have 2 of them, so we should probably focus on each of them in turn. Mass 1, mass 2. We want to know their accelerations. We're going to have to figure something out about their environmental, how they get affected. Step 2, Identify the forces that act on them. They both have 2. Force of gravity pulls down on each one. And they both get pulled by the rope. Remember, tension always pulls, never pushes. So notice that both tension forces are upward. Okay, that's step 2. Step 3, identify some axes based on the acceleration. All right, the accelerations for sure are going to be vertical. So this is easy. This is a one-dimensional problem. There's no components, skip the next step. No components. Okay, where are we? I think we finished steps 1 through 4. Okay, how about step 5? Just go ahead and plug into the equations. Well, minor twist, we don't have an x and a y equation for one object, but we do have a y equation for 2 objects. So what does it look like? It looks like this. That's it. Both of them experience 2 forces, upward tension, downward weight, and the imbalance in those 2 is what leads to those accelerations that they will have. All right, we just finished steps 1 through 5 in like a minute, except we're going to have some issues here solving this, so we're going to have a lot of the work here on the back end. So I'll do that next time. I'll start from here.